Okay, in chapter 25 now, we're going to explore a deeper connection between electric and magnetic fields. So far, we've seen that the establishment of an electric current, which is purely an electrical phenomena, produces in its vicinity magnetic fields. Somehow, the movement of charges produces a magnetic field. Likewise, we've found that moving charges through a magnetic field are deflected. So both of these connections seem to connect the electric and the magnetic. And so let's explore a deeper connection between them. We're going to use the term induced current, which are currents that are produced in a circuit by something other than something in the circuit. A battery connected to a circuit simply pushes charges through that circuit. And so the current produced by a battery is an electric current established by a power source. Induced currents are currents that appear as a result of something outside of the circuit. And so let's explore what that means. Michael Faraday was the one historically identified as the first to really explore this in detail and to make huge advances in our knowledge of the physical world, specifically with regard to electric and magnetic fields. We've seen that a current can create a magnetic field, and so one open question, which sounds like a reasonable one from a symmetry point of view, is can a magnetic field also create a current? Can it go backwards? And so Michael Faraday conducted an experiment which is depicted in the lower portion of this slide, right down here. It consists of a top circuit, which is connected to a battery by a switch, and that switch can be opened or closed. So that when open, there's no current flowing, and when closed, there's current flowing in that upper circuit. And the lower one, which simply consists of a coil connected to a current meter. Now what he found was that when the switch was open, for example, and there's no current in the coil, there's none in the lower coil either. Likewise, if the switch has been closed for a while and there's a constant current flowing in the upper circuit, he also found that there was no deflection on the needle in the lower circuit and therefore no current. But what he did find was that when the switch was initially closed after being open for a while or opened after being closed for a while, there was a deflection in the needle on the current meter in the lower circuit, indicating that closing the switch or opening the switch causes a temporary current in the lower coil. But he noticed that it only existed when there was something changing in the upper coil. For example, when we go from zero current to full current by closing the switch, there's a short period of time during which the current is ramping up from zero to its maximum value. And during that time when it's changing, there is a current induced in the lower circuit as evidenced by the deflected needle. Likewise, after the circuit has been running current for a while and the switch is opened, the transition from full current in the coil to zero current, it takes a finite amount of time for it to do that, and that change is what induces current in the lower coil and therefore deflects the needle. And it's important to note that when the switch is closed or opened, the deflection is in one direction or the other. In other words, they deflect the needle in opposite directions. So the operation of closing the switch will induce current in one direction, and the operation of opening the switch will induce the equal and opposite current in that circuit. He also found that when he wrapped the coils around a mutual iron ring, as you see in the upper right diagram, we see a battery and a switch and a coil on the left, and a coil and a current meter on the right. And he also noticed that when he opened or closed the switch in the left circuit, there was a temporary deflection of the needle in the right circuit, indicating a momentary current. He also noticed the same opposite behavior. When the switch is closed, it deflected the needle in one direction, and when opened, it would deflect the needle in the other direction. In this case, though, the two coils are connected by an iron ring, which we're going to learn can communicate a magnetic field from one coil to the other much more efficiently, because the field lines in the left coil that are produced by the current running through that circuit when the switch is closed, the field lines produced by that coil bend around and go through the other coil as shepherded by the iron ring. The iron ring basically contains the whole magnetic field. We'll learn about that a little bit later. At any rate, he did a second kind of experiment, as depicted in the lower diagram, where he inserted a magnet into a coil. And his three observations were when the magnet was still and not moving, there was no current in the lower coil, no induced current. But when the magnet moves, there is an induced current in the lower coil, as evidenced by a deflection of the needle in the current meter. So for example, when he pushed the magnet down into the coil, the meter would deflect in one direction, and when he removed it from the coil, the needle would deflect in the other direction. And so there again is a phenomena that's based on something changing, producing an induced current. And finally, he wanted to find out whether instead of moving the magnet in and out of the coil, let's move the coil in and out of the magnetic field. And so he did that. You'll notice in this diagram there is a magnet and the coil sitting in the interior of that magnet where the field is the strongest. And as long as the coil was sitting there still, there was no deflection on the needle. However, when the coil was removed, pulled to the right, there was a momentary deflection on the needle, and when he reinserted it into the field, he saw the equal and opposite current induced in that coil. So Michael Faraday found that current will appear in a closed circuit if the magnetic field passing through that coil is changing. So if you set up a circuit, a closed circuit with a coil of wire, and if there is a magnetic field that passes through that coil, it's only if the magnetic field is changing that it induces a current in that coil. And we call it an induced current because it's induced in a circuit that has no power supply based on something happening in a nearby circuit or a nearby magnetic field. Ultimately, it's the magnetic field that goes through that coil, passes through it, that generates the current. And that magnetic field only generates that current when it is changing, either increasing or decreasing, as we'll see. And the whole field of this kind of effect that an electric current being produced by a magnetic field falls under is what we call electromagnetic induction. And the key to remember here is it's change that produces the induced currents. It's only when something outside of the current or the circuit is changing that that effect happens.